בשיטות שלומדים מנטלי, אפשר לצמוד to all the methods.
Now we are going to discuss the Gaussian groups. Actually, we have developed tools we can now use again to approach this type of problems. So let me, this time, I will take a very big number. Actually, I have plans to discuss the case of a small numbers, but here, for the sake of clarity, it is better to take very big, much bigger than we actually need. So let n be odd, assume n is bigger to the power of 10. Now, we look at the group G with a set of generators. Now, the set of relators we divide into levels. R1, R2, RK, RK plus 1, etc. Where RK will be the volts of the type W to the power n, where the length of W will be between 2 to the power k minus 1 times 10, 2 to the power k times 10 minus 1. So these are the slices. So actually, for when we reach only in the force, we have comparable with the length of the volt. The periods of in the R4 will be comparable with the length of the volts in the first slice. And then it increases, so actually we have the three slices in each period. Okay. So we look on the group. These are given their relations.
Is it all words of that length or is it
All
specific
words.
All words of that length.
This is the point. All words. So we just divide them according to the length of the period. So I mean from 1 to the power 10, 1 to the power 10 minus 1, from 1 to the power 10 to 1 to the power 20 minus 1, etc., etc. So everything is divided this way in a geometric progression. Now, we will define the canonical form. Now, the canonical form is defined by induction on rank. So, I mean that we actually look on the group GK, okay, which includes the relators from the group R1 to RK, and then we look all others as elements here. They should be presented by words in the free group. This is the canonical form of rank K. So canonical form of rank 0 is just the element of the free group as they are. Then we need for group 1, I mean dividing by the first group of relators, and they should be presented as elements, etc. So we actually have the canonical rank canonical form according to each other. Canonical form in rank 1, canonical form in rank 2, etc., etc. So again, what will be the canonical form in rank 1? We do it the same way we have already defined it. Now, we take all these relators of R1 and we look on the one chart. One chart of a board just relates to subwords that are sub-relators of the first group. Maximum sub-relators well defined. And of course, so this is obviously it's closed under inverses and second permutation because the second permutation has the same length, so they are inside the same level. And then we remember our constants from 0 to 1 half. Now we will now use the length just the relative length, strictly the relative length. Just the measure is just the length divided by the length of the word. In this case, we just the simplest take of it. Lambda 0, lambda 1, lambda 2, and lambda 3, all of them with significant differences between them, which is easy to find, and tau is the threshold level. So what we do, we look on words, they should be, of course, lambda semi-canonical, lambda 1 semi-canonical. This will be the first lambda 1 semi-canonical. Then this is the first step, then we define the certified form. Certainly, the first one is by set of the forbidden word, the second for certified. It means that for each part, for each member of the chart, we are able to bring a witness that is word equivalent to this. So it is in the same one lane, but may have some differences. Here it goes this way. And then when we look on the chart of the witness, this is a one chart of the witness. So, of course, this is something on this side. There will be something in other parts. So our assumption is that this is less or equal to lambda 3. And the rest are less or equal to lambda 1 and lambda I, or lambda 2, 2 or 3. Or 1 depends now and then. We have some aperiodic sequence. It will be 1, 1, 2, 1, 2, 2, whatever. So the next one should be subject to lambda 1, the next to lambda 1, the next to lambda 2, etc., 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 and symmetrical in both sides. If these conditions are satisfied, so this is a witness. And then when a word is in its certified form, when each of its members of one chart has a corresponding witness that certifies it. And let me already say now that we have observed that if the word we are looking is periodic, then up to one period, the certified one map will be also periodic, except for some boundary. One period may be lost on the boundary because we cannot do it, but otherwise everything inside this will be as well periodic. That means that one map which is certified, all these passes that all of their one chart members are certified, it will be also periodic up to one period as ends. Now, and then we have the canonical form. canonical form is that we take the certified one map and we look the competition. If it has also the neighbor in the certified map, it may not have, but if it doesn't have, then we try all these variants. We have actually 8 ways to go with, and then 16 ways to take up to get the word on its inverse. Now, and because n is odd, so in the short legs there will be just one vector. And then the side of the vector will decide what side we will take in each case. So they're taking just the sides of the victorious in this competition in all instances, we have the canonical form. So this is the canonical form for linear words, but we can define as well canonical form of cyclic words, because here we just take a big power of it. In any case, in the periodic, we start with a periodic word and take its power is periodic, so just we know that outside some boundary effect, the canonical form will be periodic as well, so we end up with a relator, which is cyclic word, in its canonical form. So then we will have here x R1 with now when R2, 1, the canonical form of them, R3, 1, etc., RK1, RK plus 1, etc., etc. So this was our first step. Now, it is absolutely clear what we mean by this. Now, the second step. What we have to do. So then we have the two groups of relators. The first, this will take only the canonical is enough because we can all the relators express from the canonical using the R1 relators. Then we take this is a group G2 when we take these two groups of relators. By the way, it could be that the canonical word may be longer than original. By some small epsilon, it's perceivable that something that here on the boundary, it is just short enough to enter this and not this. And then when we take the uniform, it may change it, qualification go to this. So we do not care about this because eventually all these relators would be taken care of. But I'm not strictly claiming that taking these two relators and these two relators produce the sum group because of this effect that it could just cross the boundary between the second and the third letter. Okay? This point is clear.
Listen, when you take the canonical words now of R2,
Yes.
Okay, no, I don't remember. You have to take into consideration both R1 and R2.
Oh, just a moment. No, just a moment. I'm now defining this is a canonical form in rank 1. Now I'm going to define the canonical form in rank 2, and then you remark this. Yes, I only told that some of this could cross the boundary. So I'm not claiming that the group that I'm taking first to this is just isomorphic to this. Because maybe when I'm taking this, there will be escape here. And therefore, it is a minor effect, but just to have in mind that it may occur. So it will be missing here, but it will regain it when we make the next step. So ultimately, it doesn't matter. Just to know that we do not claim that the same group will be precisely the same because of this effect.
R21 is the set of canonical
R1 is a set of with the canonical words that satisfy the same length conditions. Therefore, somebody may cross the boundary and go to R3 times, that's better. Finally, it does change. Okay, now we have to define the canonical form in the second round. So, how to do this? So we are starting with a word which itself is canonical in rank 1. And we consider its two chart. Two chart, it means we look on R1 to the canonical words here, as a periodic words here, which are, as in the canonical form, as cyclic words. And we take their sub-relators, which appear, that may appear here, they may not appear, but if they appear, they may appear, whatever.
But what?
Yeah? This is two chart.
Yeah, but what was the last
This word itself was canonical in rank 1. And we look on its two chart. So, appearances of this pattern. Now, we go into the same steps. What do they mean? The first is very easy. Lambda 1 semi-canonical, just now we look on this word, it should not contain more than lambda 1 of a relator from R of this group. This is a semi-canonical. Then we have to take the certified form. So the certified form is again defined by witnesses. We have to certify this. We need a witness that certifies it. But now we have to say that the witnesses should be canonical in rank 1. We only consider witnesses as themselves canonical in rank 1. The witnesses. The witnesses. For two certified votes are canonical in rank 1. Is one canonical. And in the same way, we have their own two chart and the restrictions of the two charts imposed according to our requirements on the witnesses. Okay, then we are left with, okay, so what does it mean? Well, let me say that if we have a term, so here was a sub-relator of the word. Now, if we take this term, I mean, we replace it by its complement, that this word need not be canonical in rank 1. Because this is canonical, but we have here these angles. So then what happens here is very important. Then when we take the canonical form in rank 1 of this word, how does it look like? Okay. The point is that here we will have triangle of canonical words. This is canonical. Now it is a canonical form of it, and we have in this word is also canonical because it is a part of the period. So what happens here? We have discussed this earlier. We obtain here one possible area here, one possible area here, one possible area here. And this will be the canonical form. It goes this way, this way, this way. Otherwise it coincides with the plane term. The same on the other side. Possible there. They may be absent, but they may be present now. So now, what I know is both of them are what we called domino areas on this side and domino areas on this side. Now, what we do know that the domino areas, let me explain their structure. They appear when we have a number of appearances in the one chart, but there was strict requirements on their lengths. Actually, they would be close to 1 minus lambda 1 or 1 minus lambda 2 because they were obtained as just complements of those words that appear in the witness. And this was the restriction of the witness. Now, these words, so they're complements, because they are much bigger in their halves, therefore, when they take the final competition, they all fail. But their lengths were close to 1 to lambda 1, close to lambda 2. Therefore, the complement will be close to 1 minus lambda 1 to 1 to minus lambda 2. Up to epsilon, it doesn't matter. And then we know that this, when we have lambda 1 or lambda 2, gives us an aperiodic sequence. The conclusion is that here, this domino area cannot live on 2 periods of this, whatever. This is the important conclusion, that the domino area is confined inside 2 periods. Because 2 periods, because otherwise, when we read the sequence, we would have a square of some word here, which is excluded by our choice of the aperiodic sequence. That means that this can happen, so this between these two can be actually less than 2 periods. The same on the other side. Now, if this word is not periodic, then we have no estimate of how long it may be. It doesn't, we can, in principle, it doesn't have it. Maybe very long, who knows? But if there is another chart of the map that is periodic in its period, so it also cannot cross 2 periods of it for the same reason. So in this sense, we have a control. And this is, of course, this is a relator that belongs to R1. We consider R to be small because it should be inside the period of this. So, and this is when we take one term, or when we a number of terms, all this relate. So it means that we have a control of what happens when we take a number of terms and we take the canonical word in rank 1 after we take it. So then we have, this gives us what we call the one layer map in rank 2. So, because we take the we have now the certified one layer map in rank 2. This is well constructed. And then we know that what happened in these places are is very small by the construction in this is by the property of the canonical triangle and the aperiodicity property. Now then we take the next step and we take the competition to decide the canonical form, and then we just look on the member of the two chart, I mean the maximal occurrences of the relators from R to 1 in the corresponding path. So a number of passes, we compare between them, and the best one is declared as the winner, and the corresponding side group is the winner. So we take the pass, taking each time the side of the winner and the canonical one form of this pass. In this way, we have defined the two canonical forms. Canonical form for each word. Then we observe that if the word is periodic, we have absolutely the same mechanism of intercepting witnesses, because then if it has some word that appears, if the same member of the chart is moved by a period, so, and if it belongs to the certified, one of them belongs to the certified map, it means it has a witness with constants lambda 3. The next one will have the same constant. And then it could be used to intercept witnesses. I mean, if I have witness that also goes here, lambda 3. If we have witness that serves for this one, we move it here, and then the next one will give us the constants close to lambda 3, to some epsilon doesn't matter, and then we always, there's enough resources to escape to the safe haven. Because in any case we have a path we call the safe haven, I mean such that the estimates for all members of the chart is no much bigger than 1/2. And then the problem was that we were on the verge of our resources, we were not able to escape to the safe haven. Now, because here it is close to lambda 3, whatever we do, we're able to escape to the safe haven for the next time, and not because it was close to lambda 2, it will never violate our boundaries for the witnesses. So we know that this gives a mechanism intercepting the witnesses. If we had a witness for this, we also have a witness for every member of the chart. It is moved by a period. The conclusion is that all the certified forms are up to boundary effect will be periodic as well. Periodic 1 or 2, or one less than 2 periods, but 1 period you need. So because the certified one layer map is periodic up to boundary effect, then when we take the final competition to establish the canonical form, it is local, it only looks on one one member of the chart to the right and to the left, and then when we move a period, it's absolutely the same competition, so the same winner. So it means that if we take 2 periods on one side and 2 periods on the other side, the rest will be periodic. I mean, in particular, if we take a cyclic word and a big power, so we have also cyclic words, we're able also to define a canonical form 2 in rank 2 for cyclic words. So what we have now achieved, now we have the group R1, R21, R32, R42, etc., RK2, RK plus 1, 2, etc. This will be the second step. Now, all the rest is absolutely the same, but we only have to observe that then this canonical triangle which we obtain for the next step will be kind of fractal. Because now we have here a map of rank 3, then we will have a canonical map here. This will be in two periods here, but this also have the smaller canonical structure of the triangle, because we have here this one, and maybe this one here, and in the same way, all these times we need to take into account the middle, and it goes this way. And whatever it happens, if it means some periodic word, it should live inside 2 periods of it. But here, I don't know if this does not have some, if this does not meet some member of the 2 chart, it can be long. But when it meets some member of the 2 chart, so the 2 chart itself is a periodic word, and then it cannot be bigger than 2 periods inside this member of the 2 chart. In this case, this is actually a 2 chart. So it must stop within 2 periods of it. But if it doesn't meet periodic words, it goes infinitely. Of course, we know that because here is a periodic chart, or at least in the period, then earlier or later it will meet such things. In any case, ultimately we do the same thing absolutely with repeating in rank K. So this kind of the triangles will have kind of fractal structure subject to this requirement. It never can meet more than 2 periods of a periodic word wherever it encounters it. And in this way, we actually define the canonical form in rank K. It should be the same step. We're starting with the canonical word in rank K minus 1. We assume it should be lambda semi-canonical in rank K. Then we take it certified ranking form in rank K. All the witnesses that we use them are canonical in rank K minus 1. And then we take the computation in rank K between the elements of the chart in rank K. So the final result will be canonical word in rank K and so on. So and then it means that we have finally X and R1 and R21 and R32, etc., R K minus 1, R K plus 1K, etc., etc. So this will be the canonical form, because we take longer and longer, and these are short, so the changes will not be affected here because it can only affect long words, and these are short in this arithmetical sequence. So all this converges to a specific form of words. So this was the explanation how we define the canonical form in general rank. Now, when we have this, we are going to look on the corresponding groups. So now when we have to look on Van Kampen diagrams, so first we look on Van Kampen diagram having only this type of map. This is something very simple. So this is the Van Kampen diagram in the usual sense. It was one type of maps. So every one of them has at least many neighbors when it is in the inner map. Let us just look what we have accomplished here. Because the length of the periods will be from 1 to the power 2 to the power 10 minus 1. So this was the difference of them. So if we have two periodic words with a common part, so it means the lesson equals the length of the first period plus the length of the second period. Now, the worst case is that this is very short and this is very long. This is on one side of this level and this is on the other side. So it means that it actually could be something to the power 10 plus 2 to the power 10. 2 to the power 10 of the length of this. So actually it means that every inner ledger will have 2 to the power 20 neighbors. Because the maximum part common is 2 to the power 10 in the very big, is the worst case scenario because it has on the border a very long, this one. Then in any case, the power is bigger than 2 to the power 30, is solved with huge number of neighbors. Therefore, of course, it will have this kind of hyperbolis of convex layer structure. So when we look on this map, finally something leaving on the upper store. It is 2. Here, 2 neighbors, and this will be everything except for neighbors, even in the worst cases of this type. So it means that some very big part of the relators is on the outer boundary. In the worst case, this is precisely where we start, and we came on the other side. We have at least 2, 3 such things in any case. So this is the rank 1 case is usual small cancellation. So let us go to the rank 2 case. We now impose 2 groups of relators. Therefore, in the Van Kampen diagram, we will have 2 kinds of regions. I mean, small regions and large regions. And this actually was the case that we have considered the previous time. So this analysis applies to it. So I'm looking what is going on. We now define what I called the derived map. The derived map, we take aggregate of regions, which consists of one region of rank 2, and those regions of rank 1, the distance to this is less of the other regions of rank 1, or in the case of equality, then they have some ranking by a strength of attraction. So here will be this situation. Assume if this inner, these are original regions of rank 2. So the way that we measure them is to taking left and right transversals using the convex layer structure. So we have here, you see it may stay a region here, it may stay either on one or two regions which are closer to it. Then the left transversal always takes the left choice, the right transversal always takes the right choice. Now, these two must stand most like two waveforms. So this goes this way, this goes this way, etc. So the final outcome here, it will be also stay almost on two regions here. So this is the left transversal and here the right transversal. The same we can do here with the similar outcome. Also, we have here at most two regions. Now, when we look on it closer, then we have the following thing. That actually here the right transversal is not in the way as the picture shows, but it must go the right transversal here must go this way. And then it goes here, whatever. The left transversal will also have here two regions. And the left transversal must go along the common boundary. And the right transversal will also have here four. So the final outcome will be, if they are not close to the general boundary, we will have at most four regions of the type 1. Actually, it could be reduced to the constant from 4 to 1 to 2 regions, that means later as why. And the same will be on the other side. It means that the contribution of this common boundary when we look on the original region will just amount in this case on 4 regions of the first type. Actually, it could be even amount to reduce it to 2. So it means that it is small. And therefore, if it is an inner region, it is in this derived map, then it must have many neighbors. Otherwise, this could not fill the whole boundary. But this is on the case there were no contiguity diagram. But the important and the crucial argument here, what happens when we encounter the contiguity diagram. So this I only will show what we need to look. Now, then assume that these two attract strongly and this extract weakly. So then it will be that here we may have here a series of one layer which we call the contiguity diagram. Actually, we show here one of layer 1. It will be of distance 2, of distance 3, of distance 4, etc. Here of distance 1, distance 2, distance 3, and the similar on the other side of it. So end it here. So, and then we have to look what happens with this contiguity diagram. So after the break, we will go and discuss the contiguity diagram.
Did we argue last time that they actually coincide?
Yes, the result is that it coincides, but we will show it coincides in each rank. Not here it is just in a two-ranked map. The result will be that it coincides, that it collapses in the rank K, in the general rank.